So hello, everyone. It's my great honor to share our work to all of you. To do some performance analysis of RIS-assisted cellular network. But before I start, I would like to acknowledge the help from Professor François Bacheli and colleague from INRIA, and Luis and Stefano from Nokia Bear Labs. The agenda of today's talk is made by 5 parts. We will use an analytical tool called stochastic geometry to evaluate the network, which may not be familiar with everyone. So I will spend a few minutes to introduce what stochastic geometry is, how to use it. Then I will present how to model the RIS from a system perspective, from a signal perspective. Then I will show you RIS actually pose a new challenge to stochastic geometry to analyze the network. Then I will give you a solution. And in the rest 2 sections, I will give you some analytical and simulation results and a conclusion. So here we go. So how to analyze a network, in particular cellular network. Cellular network subject to a lot of randomness, the layout of nodes and the location of users. So imagine you are a user walking around, and all the base stations you don't know where they are. They are randomly located. Then so look at the equation at the left-right side. A user, you will receive multiple signals. You will receive a signal from the associated base station, which we assume is the closest one. And you will also receive interference from many other base stations. You don't know where they are, but they are from the area apart from the nearest base station. Here are some typical standard notation for we denote the location of base stations at a point process. Its location is X. Then the associated base station, you have a distance to that, and to all other base stations, you denote the distance. Then we use rho to denote fading, consider relay for simplicity, and the path loss function. Here, the signal also suffer from some noise. There is slight notational abuse to say the power of the noise is the power of this W. Then you see there, in this network, you will receive signal and interference and noise. To characterize the performance, we usually use SINR, this metric. So it's expressed by the power of signal divided by the power of interference plus noise. Then how to say a coverage? It means when your SINR exceeds a threshold, it's a tail distribution when it's larger than the threshold T. How to analyze it? We said there are a lot of randomness. There is a tool called stochastic geometry based on the Poisson Point Process, can give you an analytical way to compute the performance. What it means is, so you have a closest base station. So the Poisson Point Process will give you the distribution to the nearest neighbor, the distribution of R. Then for the interference from this shaded area, they are randomly located after in different scenario, you have different deployment. Stochastic geometry can give you an expression called Laplace transform of the interference. You can find it in textbook. Then for the noise, it's a constant. We just take it as a trivial. Then there is a trick in stochastic geometry. Say, once the fading follows relay, you move condition on a distance R, you move this path loss, this power to the right-hand side. Because of the fading is relay faded and its power is exponential, then you got the tail distribution can be expressed by a Laplace transform. So this tool basically says you want the coverage and it can be easily expressed by a Laplace transform. So look at the right flow chart. Using stochastic geometry, you give a density of the base station of network. You compute the spatial average of different layout of different distance. You can compute the coverage probability by the Laplace transform of this expression. You can refer that whenever you need it. Then you can obtain the ergodic rate. It's a workflow of stochastic geometry. This workflow gives you a relationship between the base station density and its performance ergodic rate. There is some research from our Mori Ahmad. They find that the ergodic rate is not always increasing with respect to the density of base station. Why is that? Is once you densify the base station, the user has higher probability to be closer to a base station, but the overall inference becomes higher. Then ergodically, the performance of the system at the system level become worse. So then RIS will come to play. The introduction of RIS gives operators a new opportunities to deploy the network, because the operators can select between base station or deploy RISes instead of base stations. From previous talk, we see the operator prefer to control the RISes by operators rather than by users. And from yesterday, you probably you recall that the RIS should be deployed as close to active nodes, either base station or users. So in our model, the Matern Cluster Process is to model the RISes clustering around the base stations. I will give you the technical description later. The right figure is an appetizer of this work. At the end, you will find how to deploy the network strategically. You can have an ergodic throughput. The strategy described here is called investment policy. It means you start with deploying base stations, and then up to a certain degree, the interference become a killer. Then you switch to deploying RISes. The metrics here is the ergodic rate. We assume the operators are always interested in ergodic rate in these performance metrics, and the return of investment is proportional to this ergodic rate. Then with this brief introduction of stochastic geometry, now we formulate our problems. What is a stochastic geometry model for considering the distributed RISes random dislocated around base stations? And in particular, how we characterize the interplay between base stations, RISes, and users. In particular, we have to do some signal processing. In section 3, I will show the difficulty arise with the introduction of RIS and how we solve that. In section 4, I will give you some results, the advantage by deploying RIS at a large scale. So now it's a system and signal models. I said we introduced the Matern Cluster Process is deploying cluster of points around base stations. So here is a technical description of what is a Matern Cluster Process. It's a two-level process. The first level is the base stations that's distributed as a Poisson Point Process, randomly located in the area. Then the second level, called Poisson Point Process, is a union of small clusters denoting the location of base RISes scattering around the base stations. Here we assume it's scattering over a ring around each base station with the inner radius with outer radius given here. Here we consider homogeneous case, means every node are considered the same. All the RISes have M reflective elements, and because the RISes have to serve multiple users in the Voronoi cell, in the cell tessellation given here. So each RIS allocate a batch to do beamforming to one user, to the typical user here. we have possible extensions, but this is somehow can be built upon the basic model. We put it at the end of the analytical part. We consider MIMO, we consider possible probabilistic blockage cases. And then we have to process the signal. We know that the signal transmitted from base station to the user and the signal reflected by different RISes goes through different passes. So there might be some delay. Then we consider the delay, and how we tackle that is given in next slide. The user is associated with the typical base station, nearest base station, and its cluster of RISes. Then we consider the RISes in other cells, right? The other cells, the other RISes have to serve their associated users. They beamform to their users. So we know that it's not beamformed to the user we consider here as the typical user. And we know from previous speaker that the beam is very small. It's 3 degree, 5 degree. So we think this randomly reflect beam is negligible. The probability that this beam overlap with this user is somehow negligible. We don't consider it in the following. This is an assumption in our model. In addition, that we know RISes are some passive reconfigurable device. So we neglect the stat lobe of this, not the main beam, the stat beams. And because it's passive, we think it's more energy efficient than base stations. That's a key difference between base station and users. There are multiple paths, right? So it's a time dispersive channel. We employ OFDM technology to mitigate this time dispersiveness or frequency selectiveness. So we send a string of signal over the OFDM block, then that's time domain is convoluted with the channel. Then we need to analyze the overall channel gain of this OFDM symbol. So this is the system model we use, is that for the associated base station and RISes, for each device, we consider a tab to denote that path. So you see there are multiple paths from the associated base station RISes. Its order is not very important because it can be taken care of by the OFDM. For the interference, we only consider the interference from other base stations. As I described in previous slides, the interference from RISes, we neglect that for the moment. And the channel for the signal targeted to this user is given by here, by path loss, by fading, by time delay, and a group of tabs from RISes, fading, path loss, and delay. In particular, here we introduce a new notation. The new random variable alpha denotes the beamformed fading from each RIS. And for the channel of interference, it's the same as the classical model. You consider all the random located RISes, fading, path loss, and delay. Then this is a bit technical, but it's a classical result from OFDM. Is for the OFDM, you map things in the frequency domain, and over all the subcarriers, you apply a matched filter. Then you get the channel gain in the frequency domain. And we know that for Fourier transform, the power of frequency is the power in the frequency domain is the power in the time domain. So actually we can sum up the power of each channel tabs in the time domain as a result of OFDM. For the interference, it's the same of the sum of channel power from all other interference. So a special attention given here is the fading for the small beams. Yesterday, we know that there is multiplication of path loss. There is multiplication of fading. So we are not physical specialists, so we use some assumptions. Here we assume the signal from base station to each RIS element it denoted by one fading rho 1 and reflected one is rho 2. Then the product is zeta. Then we know each RIS allocate a batch to do beamforming. The size is large, and when you do beamforming, the result is in-phase signal superposition. Then this alpha is the sum of amplitude of this zeta. When M is large, we can apply central limit theorem to say, okay, this fading is somehow approximated by non-central Gaussian distribution. Then, if you can recall very early about the sum of interference, aggregated power of interference built from random located base stations. Now your reflected signal is built from random located RISes. It can also be characterized by the Laplace transform. You can find it in textbook. You don't have to remember this formula. And the fading you can also find it in probability book about the Laplace transform. So what is interesting here is with the introduction of RIS, you actually make the computation between signal and interference and noise more complex, more interesting. For SINR, it's a computation of signal parts with non-signal parts. You probably imagine that a signal have to compete with a group of interference and noise. And you probably ask yourself, where's my friend, right? So now you have a group of friends called RISes, reflect your signals. It's a fair game. You have 4 players, the signal from base station, the fixed signal from RISes to compete with the signal, the interference from all other base stations, the noise. And so this is the interplay of these nodes. And the introduction of these RISes bring new challenges in analysis. We will see in next section, the performance analysis. Recall in the very early, the definition of SINR is the power of signal divided by the power of interference plus noise. So here you see the denominator is made by 2 players. The direct signal QSD, the reflected signal QSR. Condition on the distance, we want to apply the trick in stochastic geometry, means we want to convert to some Laplace transform. Then the thing we do is we manipulate these components. We assume each we assume each components behave by themselves. So you move the denominator, the interference, the noise to the right-hand side, and move your friend, the reflect signals to the right-hand side. Then we will introduce a random variable called epsilon to denote these things. Why is that? Because this epsilon is going to be easily computed by its components. This epsilon is a sum of individual random variables. And we know that the sum of random variable is a convolution, the distribution function is a convolution of each component. In the frequency domain or in the complex frequency domain, the Laplace transform domain, it's just the product of each component. I told you that for interference, for noise, for the reflected signals, these 3 components can be easily represented by Laplace transform. Then we can use the trick. We can use the trick of stochastic geometry to move the constant part to the right-hand side and try to use the exponential distribution. But here is a problem arise here, is you find the tail distribution, you actually integrate from 0 to infinity of this distribution function. Before the introduction of RIS, this epsilon is only positive. The interference and noise is some power of something, it's just positive things. And you move the reflect signal, which is a positive power, to the right-hand side. It becomes negative. It's become defined in the whole real axis. So using that trick, you find the coverage probability is represented by the Laplace transform of the positive part of epsilon plus CDF plus it's the probability of its negative part. So here is a gap. In previous slides, you get the Laplace transform of epsilon. Now you only need its positive part. We provide an analytical form solution to bridge this gap. We use one expression to map from the Laplace transform to its positive part. Here you see the notation difference is we use B to denote the Laplace transform ranging from -infinity to positive infinity. It's called bilateral Laplace transform. This L means the unilateral Laplace transform. This expression, you don't have to remember, is it looks complex, right? Indeed, it's a complex valued expression. But you look at its component, it's actually very simple. The input is the Laplace transform of positive, input of Laplace transform. The output is the Laplace transform of its positive part. From engineering point of view, input, output, very simple. Then we bridge this gap. You come back to the metrics to evaluate the network. The coverage probability you define expressed by the Laplace transform of its positive part, given in previous slides, given in previous stochastic geometry framework. Recall that that is a condition based on one specific distance. Then you compute the expectation over all distance, and the distribution of this distance is defined in stochastic geometry. You can find it in textbook. Then from this coverage probability, you go to the ergodic rate. You remember the measure we use to measure the network, the overall performance of the network. It's just it is again a function of coverage probability, an integral. Then we see now we see the takeaway from analytical part is that before the introduction of RIS, we play the signal and interference and noise. We see the signal, the power of signal give you a lever. You can leverage on it to map the problem to Laplace transform. And the interference, the noise can be easily expressed by Laplace transform. This is well-known result. Now you bring the new players RIS to the camp of interference and noise. Note the minus thing here. And this is the challenge to say now the right-hand side defined on the whole real axis. But this the Laplace transform of the reflex signals is also easily expressed in Laplace transform, right? Then you combine things together and separate the positive parts, problem solved. In our research, because now MIMO is standards and some practical concerns, we actually investigate the performance of a MIMO link. So far, we assume the base station sends signals to all the RISes and the users. We don't do specific beamforming at the base station set, but at the user side, it can combine the signals from multiple antennas using maximal ratio combining. Actually, this topic is also started without RIS. There are some results for direct signal. The fading would follow a more complicated distribution called gamma distribution. And then the coverage probability is expressed again in Laplace transform and with its higher order derivatives. In the lemma, we can bring the gap, bring the Laplace transform of positive parts and the Laplace transform itself. You can just do differentiation to find its higher order derivatives. For the reflect signals, we assume it scales with the number of receiver antennas. And for the interference, we find in our research that the power of fading would still follow the exponential distribution after the MRC, the maximal ratio combining. In practice, blockage, the real network is not very homogeneous. Some direct link are blocked, some reflecting link are blocked. So here we also consider a very simplified model that the we introduce a random variable QD to see that the portion of the direct link are blocked. We introduce a random variable QR, since the portion of reflect link are blocked. Then with this analytical framework, we can analyze this network now. We go back to the model, and now we specify the parameters. For example, we assume the density of base station is 10 per kilometer square, which is about 150 meters, the intersite distance, average intersite distance. And as a cluster ring, the size is somehow smaller than the Voronoi cell. The inner radius is 10 meters and outer radius 25. We consider somehow real network. There are multiple users, multiple RISes, which are 5 given here. We consider the number of receiver antenna as a 1 or 2. So here is ergodic rate from the previous parameters. We evaluate the ergodic rate with respect to the number of RIS antennas. When the number is 0, we mean there's no RIS exist in this network. So the y-axis depict the improvement, which is the relative value. We see that in the best case with when the user equipped with 2 antennas, you can get an average gain up to 45%. And that's subject to some condition, means the reflect link should have clear view. No reflect link should be blocked. And because we have 5 users per Voronoi cells in average, then we assume that each RIS employ 400 elements to form a small beam to the typical user. You see the gain can be high at a system level, not at one user. Another thing is we investigate the impact of blockage on the ergodic rate. From previous slide, we investigate the impact of reflect link. Now we turn attention to the direct link. For the case the direct link is blocked, we attach a penalty. That is a penalty called the blocking coefficient, like the power of direct link is paneled by some constant ranging from 0 to 10 dB. So here we only consider the RIS element is 1,000, and the blocking possibility is 50% or 75%. We see that the improvements of the ergodic rate highly depend on if the direct link is blocked or not. When the direct link is heavily blocked, like there are 10 dB penalty, you see the gain can up to 50% when the user equipped with 2 antennas. Then, because we're doing the geometry things, we try to understand influence of the size of RIS clusters. We said the RIS should be deployed randomly around base station, but how far, how close? We evaluate the outer radius as a real axis and several values of inner radius. We see that for the outer radius, with the increase of outer radius, the performance gain decreases. We see the penalty of the path loss, the 2-leg multiplication of the path loss. Then for the inner radius, it's the same. It basically says you should deploy RIS as close as possible, unless there are some obstacles there forbidden from doing so. Now we come back to our appetizers for the operators. What should operator do when you're trying to select between base stations and RISes? Here we use a metric called the ergodic rate as a metric for the return of investment. There are some value you can obtain from the suppliers, like the total cost of ownership, including the capital expenditure, the operational expenditure, I mean the license, the power consumption, the site deployment, buying assets. We just assume it's some value we can know from the market. What we do is, given this number, when we're trying to do the investment problem, we analyze the overall network. What is the density right now, the density of base station, density of RIS. Then we compute the sensitivity of the ergodic rate with respect to the change of base station or RIS. It says if you change base station or RIS a bit, how much gain you can get for the ergodic rate. So then we make a decision based on the gain and cost. When the gain cost ratio of base station exceeds the gain cost ratio for RIS, we deploy base stations. Otherwise, we deploy RISs. So that's a strategy. Then you come back to this curve is that if for a city there's no base station, you should of course start with deploying base stations. Otherwise, there's no signal to reflect. But up to a certain degree, you begin to think perhaps deploying more base stations causing more inference, and there is a diminishing and even negative return, negative gain. Then you evaluate the cost and the scenario, and when performance gain because of the RIS can be achieved in a cheaper way, you switch to deploy RISs. So this is this sequential decision-making process. It is easy to understand, and it considers the qualitative and quantitative perspective of RIS of the cost of the gain. Note that they may not capture all the uncertainty here, because in real network there are more randomness compared with this model. So here is the conclusion, the takeaway from this talk is the RIS technology can be a cost-effective, energy-efficient. It's passive devices. This can give some significant level of system level advantage, not only some link, but a system level. In particular, when the direct link are blocked, when the RISs are cheap, we saw curves that using the same resource, you can buy different amount of RISs, you can have a different gain. Or when the base station introduce too much inference, probably the only choice to make is to deploy RISs. So we see from our work, you can get analytical expression. It's somehow efficient, more efficient than simulation, and it's powerful in techno-economic analysis. So here is the talk.
Hello. Thank you for this nice presentation. Of course, as a network operator, we were looking for such kind of models to have a rule of thumb. But when I try to exploit such kind of approaches, I bump into a problem. If you go back to your initial figure with the model, with the RIS and the base station and everything, I'm wondering, yeah, the first one.
Oh, you mean this one? Or the one with?
Yeah, this one, for instance.
Okay.
Where is the environment? Where are the walls? Where are the buildings? Where are the rooms? Where are the trees?
So in this model, we consider the network is homogeneous. It's like a plane. So so the RISs can deploy randomly. When you consider the blockage, the road, the RIS would subject to this irregularity, have to be deployed somewhere. Then you have some information about the environment. So the Poisson Point Process is a model, say it can be randomly deployed anywhere.
Yeah, but do you take into account in the propagation channel models other reflectors than the RIS?
Yes, yeah. So it means a variation of the channel, right?
Like over scatterers, like.
It's captured in here, the fading of the link between base station and RIS, and the fading between RIS and user. So there is rho denotes the small scale fading that because of small multipaths around each scatters.
Now, I think that what is missing for my understanding is, RIS, you've seen prototypes, it's typically A4.
Yes.
Or 1 meter or 2 meter.
Yeah.
And the walls, so it's a fraction of the environment. And I don't see this parameter. What is the size of the reefs physically with respect of the size of the environment?
Yes, you are right. So that's why the model we use is a point process. We model the risk as a point for the moment we neglect its spatial geometry, like either A4 or disk, these things, because we only model its location and assume it can reflect signals to the typical users for the moment.
You probably make an assumption if you use fast fading channel models, RIS models, or whatever. You make some assumptions on this, the size of the risk with respect to the size of other scatterers. It's underlying somewhere.
Oh, if I understand correctly, it should be in this. It's the fading is.
Yeah. When fading, what is fading? It's multipath propagation, right?
Yes.
It's walls and clusters and scatterers, right?
Yes.
And when you say one path has the same power than a RIS propagation path, you say that the RIS has the same size as a wall.
Well, I think this practical aspect is not taken by.
It is taken into account here. If it's your underlying assumption is that a RIS is as big as a wall. This is the underlying assumption.
I think that assumption is somehow strong.
But this is what you are using.
I think you are asking about the question about the connection, the correlation between the whole elements.
It's more about if you have several paths in your model, propagation path. The power of the path reflected by a true wall is usually enormous compared to the propagation path reflected by a RIS. And therefore, I expect to see in models parameters showing my RIS is 1% of the propagation environment, or my RIS is 20%, 50% of the propagation environment. And really, I encourage people working on stochastic models, on theoretical models, to make the link between the dumb propagation environment and the smart part of it. Propagation environment with RIS are not smart, they are partially smart.
Maybe just a quick observation. I hear your question is actually two questions. One, I mean, if we have an overlaying model, I mean, for the obstacles, right, and that would produce another stochastic problem in layer to account for the obstacles. That we haven't done, so it's binary, right, with a certain probability that gets lost. So it's simple in that sense, and it's something that we are aware of. Like the second question that I have heard is, I mean, at least how I understood is, given the physics, like the practical aspects from reality, how would that be translated into the power delay profile, meaning that the power from the reflected signal would be modulated and would necessarily be lower, given that the risk is a smaller event. So yeah, that is something that we have not explicitly accounted for.
So this is missing to make it exploitable by operators. These physical parameters, fraction of environment that is made smart compared to the overall environment, and then it will be more exploitable.
But you need some geometrical implications of your model in order to be able to separate these two, let's say, factors, right? Because in a geometry-based approach, everything is together included in a final distribution. right? And
Yeah.
so it is hidden, what you're saying is hidden, actually. But to be able to split that into separate, you will need to get some advice from geometry-based modeling. Otherwise, what would you split it?
Yeah, this cooperation is missing, and I dream to see models where I have this parameter alpha, which is my assumption is X% of the environment is marked, and then this kind of result is exploitable and presentable to leaders, because it's obvious they will say, what is the size of risk we need? They ask that. Thanks.
Thank you very much, Sean, for a very good presentation. I leave the maths to you and to Francois, and I believe all that. And I would just like to understand very few things. You know, the first curve you showed that the ergodic capacity no, you go to the last slide, your last slide. Yeah, this one. You know, this red curve is without RIS.
Yes.
And the question is that you see that there's a point of inflection. How this point of inflection with the shift with the propagation constant, you know, with signal attenuation constant. If we are in a urban channel, it is like 4 to 5. But if we are in a rural channel, free space, totally, it is 2 point something. So how this inflection point will shift when we change this propagation constant?
If I understand your question correctly, you try to see the power profile of the RIS compared with the interference.
No, RIS is no RIS, RIS or no RIS. I'm talking about the red curve first. The red.
Oh, yeah,
curve.
the right curve.
Yeah, red curve.
Okay, the right curve actually depends on on some point when the base station is super dense, then the accumulated interference below very
so,
huge.
I mean, we start with let's say 20 base stations per square kilometer or something like that with the stochastic process with the distribution of lambda, BS, whatever you think.
Yes.
And we are in a propagation environment.
Yes.
And if that propagation environment is city center, we see this this point of inflection for a certain density of base station.
Yes.
How this point of inflection will shift if we decrease the value of propagation constant, if we decrease the signal attenuation.
I'm afraid I cannot answer this question.
Okay,
now because it depends on how the signal scales up and how the interference scale up. It needs some more exploration of the tool.
Okay, so next question again, very small. I think somewhere you show that M0 elements are used by the RIS for reflecting the signal.
Yes.
And you say M0 is greater than or equal to M.
Or smaller.
Oh, so the sign there is greater.
Oh, I'm sorry.
So this is just a typo. Okay, that's fine. This is what I thought. Okay, then just last question. The distribution of the base stations, the lambda,
yes,
BS is independent of distribution of RIS. I mean, you just place the RIS and this is an independent distribution. The two distributions are not correlated.
Oh, no. In the investment problem, we correlate that we think we have investments, we have some money that can buy 10 RIS, for example. if the current current density of base station is 10, then we allocate each base station one raise to that cluster.
No, but I mean, when you place 10 RIS in a cell.
No,
you
in 1 kilometer square in one area.
Yeah, and that's all random, or it is correlated with the base station distribution?
Yes, because when you buy some RIS, you distribute your RIS to different base stations. It's correlated in the model.
I see. Okay. So yeah, okay. Thank you. Yeah.
Could you please go back to slide 17, please? Here you consider that the power of the desired signal is the sum of the reflected one and the direct one.
No.
The power of the desired signal, you
Yes.
consider it is the sum of the power of the direct link
Yes,
plus
and-
the reflected from the RIS.
Yes.
Do you assume that the both signals arrive synchronized, phase synchronized and time synchronized?
Okay, so that's what that aspect is taken care of by the OFDM. The small time delay between different passes. So for example, you see here you have different delays, right? You got multiple tabs for races for the path from race from base station.
Yeah.
Then we cannot tell how much the difference, but in the frequency domain there is a nice property for the Fourier transform. Is in the frequency domain, you apply matched filter to the subcarriers, and the power of frequency domain equals to the power of time domain, right? Then the channel in the frequency domain is the sum of power in the time domain. This is Pascal's theorem in Fourier transform. So basically, we understand the channel, the superposed channel, is dispersive. There are some delays. If you consider this dispersiveness, it would be a problem in physical layer. But when we use this modulation technique, we can overcome that up to a certain degree. Yeah.
This is under the condition that there is no frequency shift when you apply your OFDM demodulation. I mean, perfectly synchronizing the.
Yes.
No frequency offset. Yeah. Thank you so much.